Hello again. This is Math 1220 coming to you from the College of DuPage, and the title of this lecture is Estimation, Approximation, Error Analysis, and Propagation. As always, be an attentive learner as you watch these videos. Sometimes you may find it helpful to know the approximate answer to a calculation. As examples, you may be in a shop and want to know broadly what you're going to have to pay. You may need to know roughly how much money you need to pay a couple of bills. You may also want to know roughly what is the right answer to a more complicated calculation and what is it likely to be, and to check if your detailed work actually is correct by comparing the answers. Whatever your precise need, you will want to know how to estimate or approximate the right answer. One very simple form of estimation is rounding. And rounding is one of the key skills. And so this is where you take a long number and make it simpler by rounding or expressing it to the nearest unit, 10, hundred, tenth, or a certain number of decimal places. For example, 1654 rounded to the nearest thousands is 2000. To the nearest 100 is 1700. To the nearest 10 it is 1650. And the way this works is straightforward. You look at the number one place to the right of the level that you're rounding it, and to see whether it's closer to 0 or 10. In practice, this means you've been asked to round to the nearest 10, so then you look at the units. And if you're rounding to 3 decimal places, you look at the 4th decimal place, and so on. If that number that you're looking at is 5 or over, you round to the next number. If it is 4 or under, you round down. So we round numbers to reduce the number of digits when keeping the result close to the original number as possible. Numbers that are less than 5 get rounded down. Numbers that are 5 or greater get rounded up. And so rounding to 1 decimal place of 1.47 is 1.5. This one rounds to 1.42, rounds to 1.4, and 1.4535, so on and so forth, rounds to 1.5. So here are some examples. Express this to the nearest 10, 156 to the nearest 10. Your answer should be 160. Express this to 3 decimal places. So 3 decimal places would be 1, 2, 3. So I look here, I get a 3, and that means it is going to be 0.456. When doing calculations, sometimes we practice what is known as front-end estimation or rounding. Front-end estimation is a way of estimating the sums, differences, or products of numbers by rounding. We first round each number to its leftmost places and then perform the operation. So for example, to add 67 and 24, I say this is close to 60, this is close to 70, this is close to 20, so 70 plus 20 is close to 90. You can also use this to get a lower and upper bound on your calculations. For example, suppose you wanted to add these 3 numbers. If you were to round these using front-end rounding but rounding them downward, you would get 20,000, 700,000, and 80,000. If you add these, you can do this in your head and get that this is around 800,000. That's the lower bound. If I round each of these numbers up, I get 30,000, 800,000, and 90,000. Again, you can add these in your head and you get 920,000. You see the actual answer is indeed between those two. So we've effectively bounded this. It works for multiplication too. Rounding down for this multiplication problem, this times this, which ends up being this. If I round down, I get 7,800. If I multiply those, I will have 5, 6, and 5 zeros. And so that's what I get. The high rounding, I would get 8,900. That way 72 and 5 zeros. And you see the real answer is certainly in between those two. You can also use this for very practical calculations. You want to buy carpet for 2 rooms. The first room is 3.2 meters by 2.7 meters. And by the way, the meter is close to a yard, and so these actually aren't that small a room, although you might not measure them in meters. The second is smaller. It is 1.16 meters by 2.5 meters. How much carpet do you need to buy to be sure you're buying enough for both rooms? Well, you round the first room's dimensions to 3 by 3, and that's going to be 9 square meters. In the second one, you have a little bit of a choice, but you could say it's about 1 meter by 2.5, so it's 2.5 square meters. So if you add the two together, you get 11.5 square meters. But you say, well, since I rounded one up and one down, I'll take that maybe up to 12. But if you get 12, you see the exact calculation is going to be 11.54. So it was a good thing that you rounded this one up, but 12 square meters was plenty. Example 2, suppose you wanted to add another room to that, and this last room is going to be 3.9 by 2.2. So what you can do is round this to 4, and 2.2 you round down to 2. Again, you have to make a choice here about that, how close you want to be. But when you add these together, you get that this is going to be 10 square meters that's added to the 12 square meters, and that means you need a total for the 3 rooms of 22 square meters. It turns out if you do the exact calculation, you get this. And so you see estimation is a real good way to estimate the quantity needed and also the cost. You also will do things, estimated time of arrival. Your GPS machine will tell you how far away from something, and it will base that on distance equal rate times time. It's calculated by a computer, but you end up doing the same kind of thing. I'll talk about an example of this. And a special case is estimating for work done, and you'll come across estimates for work to be done, whether from a builder, plumber, or someone else. In this case, the tradesperson is concerned has probably estimated how much time they are likely to take to do the work, multiplied by their hourly or daily rate, and added some additional charges for materials or a call out. They may have added a contingency for extra work needed, which is likely to be 10 or 20%, just as a safety valve for them. This means that they don't want you to be unpleasantly surprised when you get the bill. Now, an estimate is not legally binding, it's just that's what it said, but a quote is something different. If they give you a quote, they're making an agreement to do the job for that number of money. Work estimates affect both consumers and suppliers, and I'm going to give you a problem to estimate later about the exact quotes. But for now, I'm going to talk about 2 examples. One I will call piano tuners in Chicago. This is sometimes referred to as an Enrico Fermi, who was a great scientist. Fermi Laboratory in Batavia is named after him. Type of problems. And another one is a personal story. Jim goes to Indianapolis. Let's look at these examples of estimation. As a lecturer, Enrico Fermi used to challenge his classes with problems that at first glance seemed impossible. One such problem was that of estimating the number of piano tuners in Chicago, given only the population of the city. When the class returned a blank stare at their esteemed professor, he would proceed along these lines. From the almanac, we know that Chicago has a population of about 3 million people. Now assume that an average family contains 4 members, so that the number of families in Chicago must add to be about 750,000. If 1 in 5 families owns the piano, that means 1 in 5 of these, you're down to 150,000 pianos in Chicago. If the average piano tuner serviced 4 pianos every day of the week for 5 days, rested on weekends, and had a 2-week vacation during the summer, then in 1 year he would service 1,000 pianos. And so that 1,000 pianos, and we had 1,500, so 4 divided into that is going to be 150 piano tuners. So the estimate is there should be about 150 piano tuners in Chicago. Turned out at the time of this writing there was approximately 200. Now this method doesn't guarantee correct results, but does establish a first estimate which might be off by no more than a factor of 2 or 3, and certainly within a factor of 10. And so this actually ends up being a very powerful technique. And there are examples of these kind of problems that are here at this website. I'm also going to share with you a whole bunch of problems here. And I could ask you something like this on a test or exam. One of them could be, how long does it take to count to 1,000,000? So pretend that you're counting iPads in an Apple store or something like that, and it was a very large Apple store warehouse. How long would it take you to count to get to 1,000,000? I can also talk about how long does it take Jim to get to Indianapolis. So I live in Wheaton. This is Indianapolis. Now, you have to worry about, well, do I actually know exactly where in Wheaton I live and exactly where I'm going in Indianapolis? But I do have a scale, and so just broad scale, I can look at this scale and kind of carve off and figure out, well, how many miles is it along here to get to Indianapolis? And if you do that, and it really depends on how accurately you do that, but if you're doing it relatively carefully, you'll get that there are 200 miles between Wheaton and Indianapolis. If I did this trip averaging 70 miles per hour the whole way, it would take me just under 3 hours to do. If I average 50, which is the minimum speed limit, it would take me 4 hours. So you say it takes between 3 and 4 hours. The exact answer was it was 210 miles door to door, and on a good day it took me 3 hours. Again, estimation is very powerful. We can also talk about errors and percentage errors in measurement and absolute errors. So an absolute error is plus or minus 1/2 of the smallest unit on the scale of the measuring device. And we'll talk about what that is, but that is the absolute error. And the percentage error is going to be the absolute error divided by the measurement times 100%. And the percentage error is an important model. And I also wonder about what's the lowest it could be and what's the highest it could be. This is pretty much saying the same thing. So here's an example. Now units are important. So here you see liters, meters, feet, and seconds. And those liters are important because they follow along and appear in other ones. But suppose I measure something to be 9.4 liters. Well, I could be plus or minus half of the last digit. And so that is the 10th digit. So this is 0.05. 100th. Then for the minimum, what I do is I say, well, this could be as small as 9.35 liters, and I would round it to 9.4. Or it could be as large as 9.45 meters, and I would round it down to 9.4. So this is the min, this is the max. If I take this absolute error and divide it by 9.4, I get this is my relative percentage error. Okay, so you can see as you go down here, these are the calculations that are the same. Here the relative error would be 0.005, here the relative error would be 0.5, and here the relative error would be 0.0005, getting these maxes, these mins, and these relative percentages. And this relative percentage really isn't 0, but rounded to the hundredths of percent it is. So this is a very accurate measurement. I have asked problems like this, filling out an Excel spreadsheet, on exams before. Our next topic is going to be called error propagation. Error propagation occurs when you measure some quantities A, B, C, and so on, but you have uncertainties that are delta A, delta B, delta C, and so on. And you want to calculate some other quantity with a formula using the measurements of A, B, and C. Well, it turns out that the uncertainties that you have with A, B, and C will propagate, extend to the uncertainty of Q. So to calculate the uncertainty of Q, denoted by delta Q, we have the following formulas. And we are assuming that these errors are random and uncorrelated. So when we add or subtract numbers, what we do is delta X, or delta Q rather, is the summation of the square errors. And so here's an example. So we measure this as 40 plus or minus 0.18 inches, that's the length of a person, and the length of that's the length of the person from the ground to their waist, and then you measure the length of from their waist to the top of the head is 30 plus or minus 0.06 inches. You must be using a different kind of measuring device. Now suppose you use these two measurements to calculate the total height. Well, this is going to be 40 plus 30 plus some error term. So the uncertainty is I'm going to add the 0.18 squared plus a 0.06 whole squared. I'm going to take the square root of that, and that is my error. So this means that my final measurement is 70 plus or minus 0.1897. Now if you multiply or divide, the formula is different. Delta Q is equal to delta A over A squared plus delta B over B squared plus and so on and so forth. Let's look at an example. Suppose you want to measure the ratio of the length of an item A and the length of an item B. You measure the length of A to be 20 inches plus or minus 0.34 inches and the length of B to be 15 plus or minus 0.21. Well, the ratio is defined as, in this case, it is A over B would be calculated as, this would be 1.333, but the uncertainty is going to be this number squared plus this number squared, square root of all that. Do that calculation, you get this. And so the final ratio is 1.333 plus or minus 0.0294 inches. If you multiply a number times an unknown, so A is known exactly, but X isn't, then that's going to be Q is equal to the absolute value of A times delta X. So suppose you wanted to calculate the diameter of a circle as 5 plus or minus 3 inches, then you wanted to calculate the circumference, which is pi times d. Well, pi is what it is, and d, we said it was 5 meters, so that would be 15.708. But the uncertainty would be the absolute value of A, which is pi, times the uncertainty, which is 0.3. I do that calculation, I get 0.942. So the circumference of this circle would be 15.708 plus or minus 0.942 meters. If there's uncertainty in the power, what happens is so here you're having a formula that has x to the nth power, then the propagation error delta Q is going to be the absolute value of Q times the absolute value of n, the exponent, and this is delta x over x. As an example, suppose you want to calculate the side of a cube that is 2 inches plus or minus 0.02 inches. So we calculate that, we cube the 2 and we get 8 inches. But the uncertainty would be this. So here I get 8, 3, and 0.02 over 2. I do all of that calculation, I get 0.24. So the volume of the cube is 8 plus or minus 0.24 cubic inches. Now there are general formulas for air propagation, but they actually involve calculus, which is something that you haven't studied yet. This example does involve calculus, and the general topic of what we're talking about is called numerical analysis. In this class, remember that I told you never to round off until the end of the problem. Numerical analysis is a lot about what happens when you round things off. And this just shows you that the more math you know, the better off you are. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. We are all in this together. May God bless you all.